Assalamu alaikum. In today's video, I would be discussing about CIF. So what exactly is CIF? So it is a crystallographic information file, which is a text-based file format used to store information about crystal structures. It's a standardized format and plays a vital role in storing, exchanging and analyzing data within the field of crystallography. So why is it important? Up to now, what we have been doing is we have been creating very simple structures of atoms, and so there are a lot of factors that might be included here, like the angles between them might be complex, the structure between them might be complex, they might be undergoing a particular symmetry. So in case of such complex structures or unknown structures, we can take the help of a CIF file, and if we read the data of the CIF file, we can create the structure easily. So in that case, a CIF file is very important for some of the molecular dynamic simulations. So what are the key points that we need to take from here, or we need to understand? Firstly, the unit cell information, secondly, space group, thirdly, atomic positions, and some additional information. So all this would be cleared when I go through the rest of the slide. So firstly, the history and source. It is mainly designed by the International Union of Crystallography, and the source is you can download the CIF files from AMSD, American Mineralogist Crystal Structure Database, or Crystallographic Open Database. You can download the CIF files from these two websites easily. So I have taken a sample CIF file of SRTI03. So this is what a CIF file looks like when you open it with a textpad editor. So if I go through the CIF file, at the beginning you will see that there are information about the journal where it was published. Then you can find some basic information about the chemical formula, the name of the mineral, and some other numbers. So this is where the main important information starts, that the symmetry space group, this is the Hall notation, and this is the Hermann-Mauguin notation. So by the help of two notations, you are explaining what the symmetry of this particular structure is like, and then you see cell angle and cell length. So this is information about the unit cell. Also you have cell volume and all the other volumes and this. So this is also another important part, like how the symmetry operations are undergoing. This is in this part xyz, xy half minus z, and you also find there is another loop here which explains about labels, fractional xyz, and isotropic atomic equivalent. So all this is in the last part of the CIF file. So I would be going one by one. Firstly, to understand about the unit crystal. So this is a unit crystal, and the length of the cube or the length of the sides is normally the cell length, and the angle between them is the unit cell angle. So this is you see cell angle alpha, cell angle beta, cell angle gamma, cell length A, B, C. So this can be found easily from this crystal structure. Next, you have heard me talking about space groups. So what are space groups? Space groups are mathematical constructs that capture everywhere an object can be repeated through space, through translation, rotation, reflections, cruise, and gliding. That is, for example, you have a structure. So for example, you have a cube. If you rotate the cube by 90 degree, you will find that cube again. That means you are repeating the structure by a rotation of 90 degree. So this is a symmetric operation. Okay, and this is one particular space group for that particular structure. So I hope you have an idea about what space group is and what symmetrical operation is. So I would be delving deeper into the symmetric operations. Firstly, you find reflection, which is very basic. You have an original object here, you place a mirror here, and at the same distance from the mirror you would find a reflected object on the opposite side. Okay, So then you find n-fold rotational symmetry. So what does n-fold rotational symmetry mean? For the first structure, you see, if you rotate it along this axis, you can only find the original structure after rotating about 360 degree, not any less, not any more. Might be more like 700 degree, but I am talking about the less part mostly. So this is called one fold because 360 divided by 360 equals to 1. In the second case, you will see that you can repeat the structure after rotating it for 180 degree by 180 degree. So 360 divided by 180 degree equals to 2. So this is called a two-fold rotational symmetry. In the same logic, you find three-fold, four-fold, six-fold, and a infinity-fold symmetry for a circle. Next, you find inversion. So what is inversion? Inversion is mainly how you invert every point of a structure. So you see, in case of the left part here, this is a point xyz, and if you invert it, so you find minus x minus y minus z, and this is the same direction, and this is the same distance from a reference point. So this operation is mainly called inversion. Then you find translation, which is very easy to understand. Translation is mainly you moving a particular distance along a certain axis. For example, along the x-axis or along the y-axis, and it can be repeated infinitely. Okay, so this word is very important. You find glide. So what does glide mean? Glide is actually the sum of two symmetric operations, translation and reflection. For example, you have an object here and you want to make the object like this one. So what you need to do? First, you need to translate it in the upper axis, okay, along the upper axis, this axis. After translating it, then you need to reflect it. So after performing two operations, you find this structure. Okay, so this is called glide, where you have to use both symmetric operations, translation and reflection, to repeat a particular structure or orientation. Next, you find screw. So what is screw? Hope you are familiar with right hand screws. So if you make a mark on a particular thread of a screw, and if you rotate it, you will see that that mark would be at a particular direction after 360 degree, and if you rotate it by pressing it against somewhere, you will see that it will also move in the downwards direction. So this is how a screw symmetric operations work. So for example, you have an object here and you want to maintain this particular you want to repeat this particular orientation or this particular structure here. So what you need to do, firstly you translate it downwards and then you rotate it. So you see four-fold rotation. Four-fold rotation means you are rotating it by 90 degree. Then again you translate it downwards, you rotate it 90 degree, again you translate it downwards and rotate it 90 degree, and again. So finally you see that after rotating it four-fold for 4 times, which means you are rotating it 360 degree, and after translating 4 times below, you are returning to your original orientation. And this combination of translation and rotation is known as screw symmetric operation. Okay, so these are the basic symmetric operations you need to know about to understand about Hall notation and the Hermann-Mauguin notation. Okay, so next you find CIF. There are other information also, like the fractional xyz coordinate. So what does fractional xyz coordinate mean? It means that the fractional coordinates describe the position of the atom relative to the lattice parameters along the x direction, which means you are denoting or defining the position of the atoms relative to the relative to the lattice parameter and along the x-axis. Okay, so you can do it for x, y and z axis, and so you find 3 fractional xyz coordinates. Next you see occupancy. So occupancy means it mainly indicates the proportion of a crystallographic site occupied by the particular atom. For example, you have atom hydrogen and it occupies 50%, so the value you get is 0.5. okay. Next you have isotropic atomic displacement parameter, which is normally denoted by atom site u iso or equiv. Okay, so this is how it's written in the CIF file. So what does this indicate? This indicates that there is a thermal parameter for each atom, which means every atom is constantly in a state of thermal motion or disorder, which means it vibrates from a certain average position. There is an average vibration, and this particular average vibration or the magnitude of the atomic vibration, these values are normally labeled by this particular parameter. Okay, so now you have an idea of the total thing. Let's get into the particular details. So you see the symmetry space group name Hall. So we have already seen that Hall notation. We have already known about space groups. So in case of the space group symmetry, you can use two notations, Hall notation and Hermann-Mauguin notation. So firstly, in case of Hall notation, the -p indicates the primitive unit cell. There are other kinds of unit cells also. The 2c indicates that there is a screw axis along the c axis, and the 2ab indicates that there is a glide plane operation along the a and b axis. So the same thing is also denoted by this Hermann-Mauguin notation, where the p indicates the primitive cell, the b indicates that there is a screw axis along the b axis, the n represents there is a glide plane along the a axis, and the m indicates that there is a mirror plane along the c axis. Okay, so this is the same thing. You will understand more if you delve deeper into it. So I will try to link some websites where you can learn more about all these notations and everything. So you see that there's the cell angles are 90 degree each, which means it's orthogonal cell. Moreover, you have the cell length here, and you also have the cell volume and everything. Next you see the symmetric space operation, space group symmetry operation. So this part is very important. You see that there is a xyz, xy half minus z, minus x minus y half plus z, which means all the operations that the atoms are undergoing. For example, when it is xyz, it means that no operations are particularly at the moment, and then you find xy half minus z, which means that there is rotation, there is translation, and when you find minus x minus y, it means there is also inversion going on. So after all these operations, you finally find the structure from the CIF file. Okay, so why does all these operations need to be undergone? Because if you look at the next part here, you see that there are only information about 4 atoms, Sr, Ti, and only 2 oxygen atoms. But if you visualize the CIF file after converting into CFG, you see that there are 20 atoms here. So from 4 file you are getting 20 atoms. So this is not randomly generated atoms. Rather, what is happening is, after you input the information of 4 atomic files, the positions of 4 atoms, you are saying that rotate along this, rotate along that, translate along this, invert among that, and after going through all those operations, you are replicating all the atoms and you are getting the total unit cell. So you see there is also a portion about fractional x, fractional y, fractional z, which mainly indicates the position of the atoms, and also the u iso, which means the isotropic equivalent of the displacement, etc. Okay, so now you have a basic idea of what CIF files mean. So you can take a CIF file as input. So you can easily download this SRTI03 CIF file from COD, or you can use its number, which is 9002806.cif. Okay, so after downloading it and converting into CFG, you can visualize it with the help of Ovito. Next, if you download this particular file CA0.35 SR0.65. What does it mean? This 0.35 and this 0.65 comes from the occupancy. I will go into it a bit later. So, and you can also change the crystallographic orientation. So if I go here, so I am opening the CA 0.65, that particular one. Okay, so you see here CA 0.35 and the SR 0.65. This is our structure. And why is a 0.65 0.35 additionally written? Because if you look at here, you will see that all atoms except the first CA and SR have an occupancy of 1, which means they occupy 100% of their site. Okay, except for CA and SR, which have occupancies of 0.35 and 6.65 respectively, which means they occupy a fractional portion of their site. Okay, so when you replicate this, what happens is there are partial occupancies which leads to overlapping of atoms, and due to overlap you sometimes tend to lose particular or very specific information. And for this reason you cannot convert this CIF file into LMP file and get the accurate representation, and there would be a warning displayed. Okay, so let's go into the demonstrations. Firstly, I open the terminal and we go ATOMSK 9002806.cif. I convert it into CFG and our file is converted. We can visualize it with the help of Obito. Yes, so this is our file. You can now rotate it. So if I want to rotate this particular orientation, so something is very important here. The particular CIF file, this one, this 9002806, this already has a crystallographic orientation, and the crystallographic orientation of this particular crystal is like 110 minus 110 something. So how can you understand what its crystallographic orientation is? So this information you particularly get from this thing. Okay, so from all the space group information and all the symmetry operation, you need to deduce what the crystallographic orientation of this particular crystal is. So for this case it is 110 minus 110. And why is it important? Because when you want to rotate your system, okay, or when you want to change the crystallographic orientation of your system, you need to know about what crystallographic orientation is present in the crystal. So for this reason you need to know how you can deduce the crystallographic orientation from the information provided by the space group and other symmetric information. So we have ATOMSK 9002806.cif, and now you want to orient it. So firstly you need to provide its current orientation. So 110 minus 110 001. Next you put the orientation you want. So 110 010 001, and now you like cf.cfg. This is our output. You see here is a line applying symmetry operations, which is very important. You are applying symmetry, then you are getting the desired output. So if you visualize it, yes, so this is your renewed crystallographic orientation, okay, which is along all the axes you desired. Next, the other thing you need to want to work with is what happens if there are partial occupancies. So I have already shown you from the text file that there are partial occupancies. So I am taking ATOMSK 900.2807.cif. So this is the file with the partial occupancies, and if I want to convert it into LAMPS format, see what happens. See, input data contains partial occupancies which are not supported by output format. Some atom may overlap in the output file which is not physical. Okay, so this kind of error happens when you try to convert a CIF file where there are partial occupancies. So this is basically the basics of all you need to know about CIF file. Thank you.